Okay, grab a seat, get comfortable. Think of this explainer as your senior developer study guide. Today, we're diving into the exact architecture that kicked off the deep learning revolution in speech recognition. We're going to look at how we supercharged the classic, kind of clunky systems of the past to build the voice bots of the future. Now, as you step into this field, there's a fundamental truth you really need to internalize. We didn't just burn the old systems down to start over from scratch. No, we actually kept the perfectly functioning HMM, that's the Hidden Markov Model, chassis, all the states, the senones, the transition probabilities, and the whole HCLG graph sequence logic. We kept all of that. What we did do was swap out the outdated GMM, the Gaussian Mixture Model, for a deep neural network. It's literally an engine swap. The HMM still drives the sequence, right? But the DNN is this massive, new, high-performance engine determining how well each frame of audio matches a specific sound. So to understand why the old GMM engine was such a bottleneck for us, just look at how it operated. The GMM essentially forced us to model every single senone completely independently. They couldn't share any learned structures, which is horribly inefficient. And worse, it had these really strict rules about Gaussian feature correlation, meaning we had to aggressively decorrelate the inputs using mathematical transformations, stuff like LDA and MLLT. Plus, it basically wore blinders. It looked at a single frame of audio at a time. Now, compare that to the neural network capabilities. The DNN absolutely crushed all three of those limitations. We use one massive shared network that learns features across all senones jointly. Instead of forcing that decorrelation, we just feed it raw correlated filter bank features, or FBANKs, as you'll hear us call them. And honestly, the biggest game changer, we give it a wide context window of spliced frames. It can see slightly into the past and the future of the audio, which vastly increases its capacity to classify those sounds sharply. What's really fascinating here is the exact division of labor between the two systems. In the hybrid era, we have a very strict separation of concerns. As you can see, the HMM side handles the subphone units, the alignments, the decision trees, and traversing that massive HLCG graph using Viterbi decoding. The DNN side, it has exactly one job, and that's scoring. It takes in that wide context of raw audio frames we just talked about, and it outputs a posterior probability, basically the probability of a specific senone given the current audio frame. Once it does that math, the DNN simply passes the baton right back to the HMM to traverse the sequence graph. Now, I want to stop here for a second because there is a massive misconception, one I see juniors make literally all the time. Honestly, it's almost a rite of passage at this point. People think that the moment we invented the DNN, we just chucked the GMM into the nearest dumpster. But we couldn't. A DNN needs to be trained with cross-entropy loss, which means it requires a correct absolute target label for every single tiny slice of audio. But here's the catch. Raw audio doesn't just come with senone labels conveniently attached to every 10 milliseconds of sound. So where do those labels actually come from? Well, here is exactly how that pipeline builds. We literally have to use the old GMM-HMM to bootstrap the new alignments. It's a three-step dance. Step 1, you train a full traditional GMM-HM model from scratch. Step 2, you take that old model and you use it to force align your training audio, which generates a definitive map of exactly which frame corresponds to which senone. Then, step 3, you use those alignments as your absolute ground truth reference labels to train your DNN. Because without those per-frame senone labels, the DNN has zero idea what to calculate its cross-entropy loss against. So remember this, the GMM-HMM is the mandatory bootstrap, and the DNN-HMM is the high-octane upgrade we build on top of it. Which brings us to a classic interview question you are absolutely going to face, so pay close attention to this part. We've got a mathematical mismatch in this engine swap. Traditional HMM math stubbornly dictates that it needs a likelihood, that is, the probability of the audio frame given a senone state. But a neural network, by its very nature, spits out a posterior, the probability of the senone state given the audio frame. If you try to just awkwardly plug the DNN's posterior directly into the HMM's Viterbi decoder, the whole mathematical foundation breaks down. So how do we get these two totally different engines to speak the exact same mathematical language? You use what's called the Pseudo-Likelihood Trick, leaning heavily on Bayes' rule. It is super elegant, but absolutely essential. To convert that DNN posterior into a likelihood that the HMM can actually digest, you simply divide the DNN's output by the senone prior. And the prior is really just the probability of how often each senone naturally pops up in your overall training data. In practice, because we operate in log space to avoid mathematical underflow, computer rounding errors, we are quite literally just subtracting the log prior from the log posterior output of the DNN. This clever little trick gives us a scaled likelihood that feeds perfectly into the HMM, bridging that gap totally seamlessly. Okay, let's pivot a bit and dig into how this hybrid model evolved to fix one of our absolute worst production bottlenecks: speaker adaptation. Back in the final stage of the old GMM-HMM era, a stage we lovingly or maybe painfully called Try3B, we had a major, headache-inducing problem. A single GMM had to model both the phoneme being spoken and the unique acoustic characteristics of the speaker themselves. You know, whether they were male, female, had a heavy accent, stuff like that. To fix this, we used SAT, or Speaker Adaptive Training, and a feature transform called FMLR. The entire goal was to normalize everyone into a canonical speaker space so the GMM could just focus on the phonetic sound. But, as you might guess, there was a massive catch. And this catch was a nightmare for computational efficiency. Looking at the heavy, slow process of the GMM-HM, you can really see why Try3B was such a computational burden. Because think about it, you don't know a brand new speaker's FMLR transform the second they start talking. So Try3B required this horribly slow 2-pass decoding process. Pass 1, you decode the audio with a generic model just to get a rough text lattice. Then you estimate the speaker's FMLR transform from that lattice. Then, Pass 2, you redecode the entire audio stream using those adapted features. It was a massive drag. But compare that to the lightning-fast modern neural approach. We completely ditched FMLR. Instead, we use I-vectors, which is basically a 100-dimensional speaker embedding. We just concatenate this tiny vector directly to our input features. The neural network is smart enough to learn the speaker's characteristics on the fly, giving us glorious single-pass efficiency. We get all the benefits of speaker adaptation without any of that 2-pass latency. It's a real game-changer. Before we wrap up this explainer, I really want to leave you with a final thought to ponder as you gear up for the next generation of speech systems. Everything we've unpacked today, the senones, the HCLG graphs, relying on a GMM to bootstrap our frame-level alignments, all of this completely defines the hybrid era. But the cutting edge? It's rapidly moving toward end-to-end architectures, things like CTC models or OpenAI's Whisper. These completely wild architectures are attempting to drop the hidden Markov model entirely. They are skipping the senones, skipping the strict frame-by-frame alignments, and trying to map raw audio straight to text. Understanding the DNN-HMM hybrid we just went over shows you exactly why getting rid of those alignments is such a massive, earth-shattering paradigm shift. Keep that in mind as you head back to your desks. You've got the foundation now, so let's see what you can build with it. Thanks for tuning in.